Okay, since today's note has got quite a bit of text to it, I'm going to talk you through it. I'll do it in chunks. So I'll do this little video clip and talk you through this first chunk, and then there'll be a second video clip and a third video clip to talk you through the next. Kind of historically, there we go. Historically, kinematics, what we just did the other day, those equations of motion, they don't really answer the why. They just are tools to describe how something's moving. And when we say describing how something's moving, we mean like how fast, how far. So there's tools to calculate how fast, how far, things like that. Physics was kind of connected to philosophy way back when. And when people were asked why things moved, kind of a philosophical question, the answer to that is forces. Forces are what makes things move. In grade 11, you talked about Newton's laws of motion. I'm going to quickly go over them. Newton's first law of motion, kind of cool. It wasn't actually first come up with by Newton. A guy named Galileo came up with it. He called it the law of inertia. In chemistry class, you learn that the noble gases are inert, or they don't react chemically. Similarly, in physics, objects are inert. They don't react in terms of their motion. They don't, like a chemical may not go through a chemical change. An object won't go through a change in its motion unless it has to. So an object at rest is just going to stay at rest. An object in motion is going to stay in motion. The word inert I heard is like gets its roots from the same as the word lazy. Things are lazy, they don't want to change unless they're pushed to change. In terms of motion, it takes an external and unbalanced force to make something's motion change. And when we say its motion is changed, really what we mean is it's accelerated. So basically what Galileo and then Newton put in as Newton's first law is if there's an unbalanced force, that's going to change motion or cause acceleration. So unbalanced force, we're going to call it F net. If there's an unbalance, that unbalance creates an acceleration. And vice versa. If something's accelerating, then we know there must be an unbalanced force. Now what's going to pay off later in this unit is people, we actually have a built-in accelerometer. When we accelerate, we feel it. We just happen to feel the opposite. If a car is at a red light and the light turns green and the car accelerates forward, our inertia means we're at rest if we're at the red light. Our inertia kind of wants us to stay at rest. So we kind of lag behind the car. The car is connected to the ground with those nice sticky tires. The car accelerates forward, but because of our inertia, we kind of lag behind it. We stay still. We want to stay still to the seat until the seat starts pushing us forward. So it feels like we're pushed backward into the seats of our car, but really what happened is the car accelerated forward underneath us. So we can feel that acceleration, we just feel the opposite. If it feels like we're thrown backward or pushed backward, really what happened is the car accelerated forward. Similarly, if it feels like we're thrown forward, so imagine this, you're in a car and you feel pushed forward. If you feel like you're pushed forward, really what happened is the car was slowing down or accelerating backward. What we're going to get to next week is the physics of turning. If a car turns, I typed it up as a car turning to the right. If a car turns to the right, here, let's do a little top view. Say this is a curve in the road. This is a top view of your car. It's a convertible, so we can see there's your head right there. If the car turns to the right, that means the car's going to follow that path. The car's going to end up over here. Your inertia wants you to keep going in your straight line. You don't want to deviate or change from that straight line. Pretend that's a straight line. You want to keep going in that straight line, but the force on the car, had the car move to the right, you're going to move to the right with the car, but because of your inertia, you feel like you're pushed outward. There's no real force there. It just feels like you're pushed outward because of your inertia. Oops. That'll come up next week when we talk about the physics of turning. You always feel the opposite of what's happening. If you feel pushed to the left, that must mean the car's pushed to the right. Cruising right along, Newton's second law is the math of Newton's first law. In Newton's first law, we said if there's an unbalance, that's going to create an acceleration. Newton's first law just connects those two. F net is just the math for how big the unbalanced is, and that calculates out what acceleration we're going to get out of it. A neat thing when we think about Newton's second law is it kind of redefines mass. We usually think about mass as connected to gravity. How much mass we have dictates the gravity force on us. Sometimes physicists call that the gravitational mass. There's this version of mass as well. Mass connects the unbalance to the acceleration. Sometimes people call that the inertial mass. They calculate it out to be the same way. If you were to figure out something's mass by taking advantage of gravity, you're going to get so many kilograms. If you were to build some crazy machine and calculate mass based on a net force making something accelerate, you could calculate, like if you knew the F net and you knew the A, you could calculate the M. You would calculate the exact same number for mass. They're found different ways, but they work out to be the same number. The other thing we did in grade 11, just as a refresher, is we spent some time looking at vertical accelerations, like questions in elevators, and we, after that, having learned about the normal force, we used that with the coefficient of friction and did a better job calculating and quantifying friction. I'm not going to use this video to answer these two questions. There's already video links there, but maybe pause, take a look at those two questions, see if you can do them on your own, check my solution. The second one, I did an embarrassingly dumb algebra mistake, so when you're watching the video for the second one, see if you can find my dumb algebra mistake. I haven't got around to redoing that video, and at this point I think I'll just let it stand with the mistake in it and make it a challenge to you to see if you can find the mistake. Before we pause this video just a little bit more, in grade 11 you also learned Newton's third law of motion. Newton's third law of motion is that simple one: for every action there's an equal and opposite reaction. It's kind of a cool one. If you push on something, even something inert like a wall, the wall is going to react and push back on you. If you push on a wall, if the wall could move, it would move, let's say, forward, but by Newton's third law, the wall reacts and pushes backwards on you. If you're on ice or something, you might slide backward. If you ever watched any fails of like people falling off of paddle boards, it's usually a Newton's third law thing. They step forward and the paddle board, since it can move, it moves backwards. If you watch any SpaceX launches, that's all Newton's third law. They jam these rockets full of gas, light it on fire, so there's a huge force pushing the gas downward out of the rocket. That downward force has a reactionary force that pushes the rocket upward. Newton's third law wasn't a huge thing in grade 11, but we're going to come back to it later this quadmester when we tackle something called momentum. Conservation of momentum, the law of momentum, is sort of the math related to Newton's third law. That's where I'll pause this video. If you haven't yet, take a look at those two questions on Newton's second law to make sure grade 11 Newton's second law sticks, and then push on and watch the next video where you learn new stuff for grade 12.